Welcome to this next video in the measurement series. We're going to be looking today at volume now of prisms and cylinders. You've probably noticed that we've gone from length through to area, now we're extending out into volume. Okay, so your learning goal for this one is that students would solve problems now relating to the volume of prisms and to be able to convert between different units of volume, obviously. Okay, so you'll be able to, at the end of this, calculate the volume of some given cylinder and convert between common units of volume. Okay? Right, we're going to now go into the third dimension, which, funnily enough, we live there anyway, so you'll be fine. But let's bust out another Cartesian plane for ourselves, and we're about to extend this. Okay, there we go, and move it out here, and we will. So here, this is our x direction, this is our y, I showed you it before. Now I've drawn it out here because if you can imagine this going into the page this way and then coming out of the page this way, this is our z dimension. Okay, now that's our three dimensions of sort of space that exist around you. There's forward, back, left, right, up and down, that kind of thing, and all exists. So this is now another Cartesian plane, it's sort of a Cartesian volume, all right, so Cartesian space. Now z obviously goes this direction as well. Now, because remember we started by having a point, which was a zero dimension, then we can join 2 points like that and have one dimension. Then we could, remember, extend that line up and now have a 2 dimensions, this area. Well, the way I want you to think about volume is that volume is like we've got an area and it has been extended into that third dimension. Okay, and so this area has been pushed back this way into that third dimension there. Okay, all right, and hopefully you can kind of see that. So that area is like chunked the whole way down. This is exactly what a prism is. A prism is a certain face, a shape, a basic face area that has been extended back. And so if you came along and randomly decided to cut this shape through here, you would get exactly the same shape as it's on the front here. Okay, and so when I talk about volume later on, we introduce a particular formula to you that a volume is equal to, or a prism especially, is equal to some area times a length in that z direction. Okay, so we've got an area times by this third dimension we're multiplying by. All right, you're free to learn it that way. You're free to go with some other ones if they sort of work better for you, but I want you to sort of grasp that concept that that's where volume's coming from. Okay, so some key ideas. We can convert between different units of volume like we have been able to convert between different units of length and time and that kind of stuff. Okay, so we'll use our little ladder formula the way that we usually do. Okay, now you remember if we, it's a bit naughty, I've left the squareds on there. Because we have 3 dimensions, so because we have the 3 dimensions there, it means that we've got to have our cubed up here because it's a length times a length. Length times the length times the length, so that means we're going to have, you know, a length cubed. All right, so that's why we've got kilometers cubed here. Now, you remember, it was 1,000 to go from kilometers to meters. Okay, we're multiplying by 1,000 to go from kilometers to meters. But now, because it's kilometers cubed, we have 1,000 cubed to go that way. Okay, again, from here to here, we're multiplying. We've got meters cubed through to centimeters cubed. So that's going to be 100 cubed. Centimeters cubed down to millimeters, still multiplying, and this now is going to be 10 cubed. All right. Again, we divide and we're going back up this way. And from meters, kilometers, well, there's a big line there. Okay, dividing that way. So just remember this cubed nature when we're using our volumes, because you can't. I guess you can sort of picture it without. If we had a meter cubed here, cubic meter. It's a cubic meter because there's 100 centimeters going this way, and 100 centimeters going this way, and 100 centimeters going this way. So that means that's why there's 100 times 100 times 100, lots of centimeters cubed inside that giant meters cubed. And so if we now have a look at capacity, is something a little different. So volume is just an amount of space, whereas capacity is the volume of fluid or gas, you can see it, that a container can hold. So like a carton of milk or something like that. All right. Now, because it's not necessarily about space so much, it doesn't have any cubes in the units or anything like that. Okay, and so we can convert between these different units pretty easily. And the four that you're going to use the most are, this first one here is megaliters, kiloliters, liters, and milliliters. So I might write this out to the side here. So this is megaliters, kiloliters, and liters and milliliters. Okay, now you should be able to figure out the kiloliters to liters. That's by thousands. Times and divide. Our liters down to milliliters. That's also times 1,000 and divide by, going this way. Now, a megaliter is 1,000 liters. That's what the big M out the front means. And to go from kilo up to mega, whoops, to go from kilo up to mega, it's also by 1,000 as well. And we times or divide depending upon which way we go. All right, so it's pretty easy to go that way. Now, something you'll need to probably recognize is that 1 kiloliter is 1 cubic meter. Okay, so there are 1,000 liters inside a cubic meter. All right, so you times liters by 1,000 to get to cubic meters. All right, so that's the sort of the main conversion between the capacity and volume that you'll need to make. Okay, all right. A prism has exactly the same cross-section as the base it's projected from, as we talked about before, and we're going to go through some common formulae for some of the common prisms and a cylinder as well, because technically a cylinder isn't a prism, although it behaves very similar. Okay, so a cube is usually we're going to have a side length, side and a side, because remember these are all the same at the front here, and it turns out it's been projected by exactly the same as well. All right, so if our area of our prism, if our volume is equal to some area times a projected length in that z direction, remember area of a square is side squared times the side that is going back now, so the volume of our cubed is equal to side cubed. Okay, the side length of that cube cubed. All right, okay, our rectangular prism. Now usually we're going to go length times width times depth or height, doesn't really matter how you go with it. Okay, so if our volume, as we've been using with our generic formula, so volume is equal to the area times that projected length. So our area of this front piece here, okay, is going to be this length times this width. Okay, length times width times the distance it goes back, which is that depth. Okay, so length times width times depth is another way you can talk about the volume. All right, doesn't really matter, length times width times depth, base times width times height, however you're going to go with it. Just that idea that you're multiplying a certain area by that distance that's being projected. Okay, our triangular prism. So with our triangular prism, we need to think that as well. Like, again, go straight for that volume is equal to some area times that projected length there. Right, the area we're talking about is this area of the triangle on the front here. Now, it would usually be given as well this perpendicular height. Okay, so, and we've got this base length here and some depth that it's been multiplied back. Okay, so our area is half base times perpendicular height times that depth. Okay, and so that will be our volume of a triangular prism, this formula here. Okay, now finally the cylinder. Again, we're going to use our same formula, generic formula for a prism, which is the area of the face times the z dimension it's multiplied back. Now for a cylinder, we usually be given some kind of radius at the front here, and then this length here, which we'll again call a depth. Okay, so the area of that circle at the front would be pi r squared times the depth that it goes back. Okay, so again, as I said at the start, I don't really want you to try and remember all of these formulae. It's going to be difficult to do that perfectly, and you don't want that kind of hassles for you in exam situations and stuff. So I highly recommend thinking about volume of prisms and the like, being finding out that area of the face at the front and then multiplying it by the distance that it gets pushed back, okay? So I hope that's been good for you, maybe some revision, some stuff that you haven't seen before, and you'll get plenty of time to practice that in class. So look forward to seeing you at school. Thanks.